Assalamualaikum and a very good day. Uh, we have finished on the Mac commissioning, okay, and the last part of the Mac commissioning is the laser Mac commissioning. Now I will proceed with another section, which is the thermal oxidation of silicon. If you remember our slides, okay, on the photolithography, there's one insulation layer above the silicon layer. Okay, so silicon dioxide is one of an important insulating layer in microfabrication. Okay, so how you are going to uh, oxidize? Okay, how you want to uh, make sure that you can get the silicon dioxide. One of the way is to react the silicon wafers with oxygen atom at high temperature, which is usually more than 900 degrees Celsius. Okay, so the most important part of the slide is that the setup of the uh, thermal oxidation of silicon equipment. Okay, the setup. So you have the oxygen supply. Okay, the bubbler with water, which is kept at above 95 degrees Celsius. Then you have the tubing, okay, made from quartz, which has the wafers, okay, and then you have the resistance heating. So you will control, okay, the heating of the wafers, okay, that the oxygen will be supplied, okay, to the wafers. Okay, so what happened during thermal oxidation? Okay, on the wafer surface, a layer of oxide is formed, okay, during the heating. Okay, you can see the oxygen, and then this will separate the interior silicon with the oxygen atom. Okay, then in this reaction, the atoms outside will diffuse through the oxide layer, okay, and react with the silicon on the inner interface of the silicon and also the oxide. So from the time goes on, okay, the thickness of the oxide grows, okay, and the oxidation rate, okay, saturated. And okay, so the deposition rate and thickness of the silicon dioxide depends on the temperature. Okay, for this section, we will learn about the metal deposition of the samples. Okay, there are a few methods to deposit the metals. Okay, there are thermal evaporation, electron beam evaporation, and also sputtering. Okay, in slide 65, we will be exposed to the thermal evaporation. Okay, thermal evaporation is usually to deposit aluminium. Okay, among the metal used in microfabrication that is easily to be deposited is the aluminium. Aluminium is relatively easy, okay, to be vaporized because of its low melting point if we compare to the other type of metals, which is just around 660 degrees Celsius. Okay, so a typical system of a thermal evaporation, okay, it needs to be under high vacuum, okay, because we don't want any oxygen, air, okay, oxygen and oxygens and moisture inside the chamber. Okay, so how does it work for this thermal evaporation? Okay, so we will have large electric current, okay, that will go through the aluminium charge resistive by using aluminium charge resistive heating mechanism. Okay, so this large electric current will makes the aluminium to evaporize. Okay, to vaporize. So what happened next is that the aluminium vapor, okay, will reach the wafer surface, recondense, and then this will form a thin aluminium film. Okay, so this is just like how water evaporize, okay, goes up to the sky, okay, and then becomes the cloud. Okay, quite that is the simplest explanation how does the system, okay, how the system works. Okay, so I hope all of you can study the diagram. Okay, the diagram. Okay, you in your diagram you need to have the high current source. Okay, you need to have the aluminium chunk there. Okay, and then the pressure inside. Okay, and lastly, okay, you need to have also your wafer. Okay, your wafer, and then also the chamber. Slide 67, okay, tells us on the how you are going to control, okay, the deposition rate, okay, and also the disadvantages of using the system. Okay, so how you are going to, okay, how you are going to control the deposition rate. Okay, so it will be related to the heating power. Okay, and this is controlled by the electric current. So if the current is high, okay, then the deposition rate will be high. Okay, so another points, okay, that you can have a look into the slide is that, okay, although the system is simple, okay, the system is simple, the mechanism is sound, okay, is logical, okay, but then one of the disadvantages is that it has a significant trace amount of sodium. Okay, it has a low deposition rate compared to other type of metal deposition mechanism. Okay, then it has a poor stack coverage. Okay, so if it is intended to deposit alloy, it won't be that good. Okay, and usually if you want to do a very large scale, okay, very large scale, yeah, VLSI, okay, it is no longer used. Okay, but this system, if it is just for just what I call just for a study, okay, for like test of proof of concept, okay, sometimes it is still be done. Okay, slide number 68 is about the electron beam evaporation. Okay, so just now, okay, about the thermal evaporation. Okay, you just heat up the aluminum crucibles, and then you will have your aluminum being evaporated. Okay, so what are the difference of this electron beam evaporation and also the thermal evaporation? Okay, so here what happened, now we tell you the mechanism first, which are the, okay, and electron beams, okay, a beam of electrons typically with the energy about 10 kilo electron volts, okay, and the current up to several amperes is directed at the metal. Okay, it can be many type of metals, titanium, okay, aluminium, okay, there can be the few other type of metals, okay, is directed at the metal in a water-cooled crucible in vacuum chamber. Okay, this process heats the metal to the evaporation temperature. Okay, then okay, the vapor of the metal, okay, will be vaporized, okay, and then it will deposited on the wafers. Okay, so to improve the step coverage, what is done is that you will use the infrared lamp, okay, to heat the wafer to improve the step coverage. Okay, have a look on the diagram of the how the setup for the electron beam evaporation. Slide 69 is a simple slide. Okay, it just tells you about the advantages of using electron beam evaporation technique. Okay, so you will have a better step coverage. Okay, why? Because it has a higher surface mobility due to the the infrared lamp heating. Okay, it has less sodium contamination. Okay, however, the quality of the e-beam evaporation technique is a bit lesser than is less than the sputtering deposition technique. Okay, so if you want to have a high quality metal deposition quality, okay, it is not used in advanced semiconductor fabrication lab. Okay, slide number 70 is about sputtering. Okay, the last technique is sputtering. What is the meaning or definition of sputtering? Okay, sputtering means ejecting material from a target. Okay, you can see in the diagram, you have a sputtering target. Okay, there is a source onto a substrate. Okay, so you have your substrate there. Okay, so how does it done? It is due to the bombardment of heavy ions such as argon ion. Okay, so sputtering is the most commonly used pressure vapor deposition process to deposit metal. Okay, it involves energetic ion bombardment which physically dislodge dislodge the atoms or molecules from the solid metal surface, usually from the target, and deposit them on the substrate as thin metal film. And usually we will use argon ion as a sputtering atom because it is a sputtering ion or sputtering atom because it is inert, relatively heavy, abundant, and cost effective. Please refer to the diagram. Okay, you see the cathode. Okay, you see the anode with a substrate. Then you have the plasma. Okay, you have the target. Okay, you have the argon gas feed through, and so on. Okay, so by referring to the diagram, please also refer to the those sentences in the slides. So here, when power is applied between two electrodes under low pressure, a free electron is accelerated by the electric field. So these free electrons will collide with the argon, and then this will create another free electron, and here the argon will become positively charged. So this cycle will be repeated, and then there will be more electrons, and then it will create more argon ion. So what happened next is that the positively charged argon ions are accelerated towards the target, which is negatively biased. These energetic argon ions hit the target surface. Atoms of the target materials are physically removed from the surface. Then it will throw thrown up into the vacuum, okay, in the form of metal vapor. Then the sputtered of atoms will leave the target and travel inside the vacuum chamber in the form of metal vapor, and they will reach the wafer surface, absorb, okay, they will got onto the surface of the wafer and becomes atoms, okay. So they will start to recondense and everything, and they form grain, okay, and they start to grow, and they will continue to become the metal thin film on the wafer surface. Now we are going to finish, okay, the topic of microfabrication. Okay, the final topic will be the wafer bonding. So for wafer bonding, you want to join two wafers together. Okay, so here you will allow the design and fabrication of multi-level devices assembled from the machining of separate wafers. Okay, although the actual mechanism is not fully understood, but this relies on the formation of the silicon silicon bonds between these wafers. Okay, do look into at the diagram, okay, about how you are going to bond two wafers together. You can see the glass, fritz seal, and so on. For slide number 76, okay, it shows how wafer bonding is done. Okay, the most important part here is the silicon dioxide layer. So if we heat it up more than 700 degrees, we have a silicon dioxide there. Okay, it will be bond, and there are two types of bonding that is important, which are the silanol bond and also the siloxane bond. Okay. Slide number 77 shows you the fusion bonding procedures. Okay, so first of all, you need to do the surface treatment to make the hydrophilic surfaces, okay, by soaking the wafers in piranha solution. Okay, this will create hydrophilic top layer, which consists of hydroxyl bonds. Okay, then we rinse and dry them. Okay, this self bonding is formed throughout the wafer surfaces without external pressure with considerable forces, and the final step is that to annihilate at more than 800 degrees Celsius, okay, in oxidizing or non-oxidizing environment. Okay, so here what will happen is that the water molecules will come out, and then the voids, okay, the voids between the layers, okay, will be observed, okay, after 200 degrees Celsius. This voids, okay, tends to disappear, and the bonding strength is increased, okay, after 300 degrees Celsius, forming siloxane bonds. Okay, at higher temperatures, okay, after 800 degrees, oxygen at the interface may diffuse. Okay, this will form the silicon-silicon bonds like single crystal silicon at above 1000 degrees Celsius. Okay, apart from the fusion bonding, there's another strategy that you can use, okay, to do wafer bonding. Okay, here is the anodic bonding, where you manipulate the strong electrostatic force, okay, where you pull these two surfaces of the wafer together, and then this will form an intimate contact. Okay, in addition, okay, the natrium ions start to drift to the negative electrode. Okay, then this will create depletion zone adjacent to the silicon, which is the positive electrode. Okay, so here during the charging process, the electric field is high enough to allow a drift of oxygen to the positive electrode, reacting with the silicon and creating silicon oxygen bond. Okay, so the advantage of this mechanism is that it is done under much lower temperature, which is around 300 to 400 degrees Celsius. So by referring to the slide number 79, okay, you can see that we have a silicon and then the glass and also the silicon, okay. So we put together this setup, and then the glass is okay. So how the glass is put onto the silicon surfaces, okay. You sputtered the glass, okay. By using the setup, okay, the bonding will take place at 300 to 400 degrees, and the voltage used is around 50 to 100 to 1200 voltage, okay. And finally, we come to our final slide, which is slide 80. Okay, this tells you about the summary of the anodic bonding. Okay, the summary of the anodic bonding. Okay, you need to consider all the typical variables. Okay, the general conditions, the requirements, also the benefits. Okay, so like I told you, for anodic bonding, the advantages are, okay, it is done at the lower temperature. And then another important point is that it is less stringent. Okay, the requirement is less stringent for the surface quality of the wafers. So I would like to end this lecture with a lot of thanks, and thank you, okay, for your cooperation.